The next topic we'll look at in section 4.2 is on the domains of logarithmic functions. Now, the last topic we looked at was at graphing logarithmic functions. And when we graphed a basic logarithmic function, such as log to the base 2 of x, what we saw in the graph was that the domain of the logarithmic function was all values from 0 to infinity, but 0 was not included. Remember, we had a vertical asymptote at x equals 0, and the range is minus infinity to infinity, which of course has been switched from our domain and range for our exponential function. So we saw this graphically. When we look at the domains of logarithmic functions, well, for a basic logarithmic function, log to the base b, of just a simple input of x, the domain is all positive real numbers. In other words, x must be strictly greater than 0. And we see that relationship here with the parenthesis in our interval notation. We will get to the common and natural logs at the end of this section. But if you were to input a negative value or the value of 0 and say hit the log button on your calculator, you would get an error because it would violate the domain of the logarithmic function. Now, we can extend this definition to more sophisticated logarithmic functions where we have log to the base b, and instead of just a simple expression like x, it may be a more complicated expression that your text will refer to generically as g of x. But essentially the domain restriction is the same. This input into the logarithmic function, whatever it is, g of x, must be strictly greater than 0. So notice we really have the same mathematical relationship. Whether it's just plain x or some expression g of x, the values must be greater than 0 to be a valid input to the domain of the logarithmic function. Let's look at example 7 on page 484 of your textbook. So now we have f of x equals log to the base 4 of x plus 3. So notice, this isn't just plain x, it is some expression g of x. So here, g of x is equal to x plus 3, and now this must be set greater than or equal to 0, as we saw with our definition here. So to solve now for x, I will subtract 3 from each side. Here, x must be greater than minus 3, and in our domain notation, that would of course be minus 3 to infinity. This example also connects with the last topic we looked at, which were transformations of logarithmic functions. If you look carefully, you'll see that this plus 3 here is inside the argument of the function. That is a horizontal shift left 3 units. Figure 4.13 in your textbooks shows the graph of this function, and notice, because of the horizontal shift, the graph has been shifted left 3 units, and the vertical asymptote that originally would have been an x equals 0 is now x equals minus 3. But again, our domain is all values from minus 3 to positive infinity, not including minus 3 itself. Let's look at example 10 on page 487 of your textbook. And here, they're going to give us a function f of x equals, and this will be the natural log function that we're going to look at shortly. The natural log function is the logarithmic function with a base of the natural base e. But we're just going to focus on the domain for now. So we have natural log of 3 minus x. Our expression g of x is 3 minus x. And again, that must be set greater than or equal to 0. So now, to find the domain of this function, we have 3 minus x greater than 0. I'll add x to each side. So this inequality will be 3 greater than x. If you want to turn that around, you can. That's x less than 3. And so in our domain notation, that will be minus infinity to 3. In part B, we have another example involving the natural log function. We have natural log of x minus 3 squared. So now our expression g of x is x minus 3 squared. And again, we need to set that greater than 0. Now, you may think you would take the square root of each side and then solve and eventually get x greater than 3. However, if you look at the expression closely, this one's a little trickier because of the square. Remember, any input into our logarithmic function just has to be positive and greater than 0. So because of the square, any negative value will become squared and become positive, and almost every positive value can be substituted into this expression and will be a positive quantity greater than 0. There is one value that must be excluded, and this is x cannot equal 3. If we substitute x equals 3 into this expression, 3 minus 3 squared would of course be 0. That is not greater than 0. So this is a slightly different example where there's actually just one excluded value. So we'd have minus infinity 3 joined with 3 to infinity. Now, do pencil problems 6 and 8a. The last topic we'll look at in this section is on common and natural logarithms. And these are somewhat specialized logarithmic functions that are commonly used. The first is the common log function. This is the base 10 logarithmic function. Remember, normally we see logarithms written with this subscript, which clearly identifies the base. However, the base 10 log function will be written with just the word log. So if you see the word log and you do not see the subscript, it's implied that you understand it's the base 10 or common log function. And then we have the natural log function. Again, that is the base E logarithmic function. So again, normally we would have our logarithm written like this, where you'd see log and the subscript would show base E. However, that is not how you will see it written. You will see it written as ln, or natural log of x, and thus it's implied that you understand that the base is base E. And you also see in your calculators, you will have two buttons somewhere on your calculator that will say log for the common log function and ln for the natural log function. All the properties of logarithms that we looked at earlier in the chapter, those two groups of properties involving one and the inverse properties, can be made more specific, but are the same for the common and natural logs. You can look on pages 486 and 487 of your textbook to see those properties applied to the common and natural logarithms. Like many of the functions we've studied in our course, these functions can be used for modeling. Namely, we can use common and natural logs to create mathematical models of processes or situations so we can better understand them. Let's look at a couple examples of modeling with the common log and the natural log. Example 8 on page 485 of your textbook shows a logarithmic model that models the height of children. And logarithmic functions can be very good at modeling a process that has rapid initial growth and then slows over time, which of course is true for growth of any human being. We grow very rapidly when you're younger, and eventually you grow less and less as you become older and become an adult. So this model is the percentage of adult height attained by a boy X years old. And so we see our model f of x is 29 plus 48.8 log of x plus 1. The age of the boy has to be between 5 and 15 for this particular model. But the question asks us, what percentage of adult height has boy attained at age 8? So for this particular question, we're asked to evaluate this model function when x is 8. So finding f of 8, we'll have 29 plus 48.8. And now where I see x here in the log expression, I'll put 8. So we really have 29 plus 48.8 times the log. Remember, that's the common log of 9. So using your calculator, we'll get approximately 75.56 or 76%. Just remember, depending on your calculator, some calculators you can enter this expression directly. Others, you may need to evaluate log 9 first, then multiply by 48.8, and then add 29 to get the correct final answer. Let's look at an example involving the natural log function. Example 11 on page 487 of your textbook models the dangerous heat increase that can happen inside an enclosed vehicle. And so this model models the temperature increase in degrees Fahrenheit after X minutes. Especially when the weather is very warm outside, that can happen quite quickly and be dangerous. So now our function is f of x equals 13.4 times the natural log of x minus 11.6. And the problem asks, find the temperature increase after 50 minutes. Like our previous example, we need to evaluate this model and the function at a particular value of x, in this case 50 minutes. So finding f of 50, we get 13.4 times natural log of 50 minus 11.6. And that will equal approximately 40.82 or 41 degrees Fahrenheit to the nearest minute. Again, just make sure you know how to use your particular calculator. You might have to calculate natural log of 50, multiply by 13.4, and then subtract 11.6 to get the correct answer. Now do pencil problems 7 and 8b.